Did you know? There was a monumental debate in the history of science. It was not fought on a battlefield filled with smoke, but rather it unfolded intensely before blackboards. The opposing sides represented some of the greatest minds in human history, Isaac Newton and Christian Huygens. Their debate centered on a single fundamental question: is light a particle or is it a wave? Newton firmly maintained that light consists of particles. Huygens, conversely, insisted that light is a wave. The two debated this for their entire lives, with neither able to convince the other. Ultimately, it appeared that Newton had prevailed. However, this was not because his theory was correct, but rather due to his immense reputation. The entire physics community was led astray by Newton's influence, persisting for over a century, until the year 1801, when a figure named Thomas Young emerged. He conducted an experiment that instantly challenged Newton's authority, demonstrating that light is, in fact, a wave. Yet, the story did not conclude so simply. By 1905, Albert Einstein emerged with the assertion that light also behaves as a particle. Light is both a wave and a particle. Does this not seem contradictory? Yet it is accurate. 1. This is one of the most counterintuitive conclusions in physics. 1. This conclusion fundamentally shattered our understanding of the world, for it reveals to us that, in the microscopic realm, conventional logic no longer applies. To comprehend this extraordinary conclusion, we must rewind to the 17th century. 1.5. At that time, humanity began to seriously ponder a question. 17.0, 16, 20.0, 1.6, 4.0, 8.0, 8.0, 16.0. What exactly is light? Newton proposed that light consists of countless infinitesimal particles, streaming from the sun to the earth like projectiles. This theory could explain numerous phenomena, such as why light travels in straight lines, and why it undergoes reflection and refraction. Newton, in the physics community of that era, held a status akin to a deity. When he stated light is a particle, everyone simply accepted it. However, the Dutch physicist Christian Huygens disagreed. He proposed that light is a form of wave, propagating through space much like ripples in water. Huygens' theory could also explain many phenomena, but unfortunately, Newton's reputation was too dominant and his voice went unheard. Throughout the 18th century, the corpuscular theory reigned supreme in the world of physics, until the arrival of Thomas Young in 1801. This British scientist conducted a remarkably simple experiment. He cut two narrow slits into a barrier and directed a beam of light to pass through them. If light were composed of particles, then after passing through the slits, two bright lines should appear on the screen, similar to bullets passing through two holes. No. 87-94921-2225. However, the result astounded everyone. Instead of two lines appearing on the screen, but rather a series of alternating light and dark bands, resembling the stripes of a zebra. This phenomenon is known as interference, a property exclusive to waves. Consider casting two stones into water simultaneously. The resulting ripples superimpose upon one another. Where a crest meets a crest, the energy is amplified. Where a crest meets a trough, the energy is cancelled out. The interference patterns of light prove Newton wrong. Light is not a particle, but a wave. Thomas Young's experiment is cited as one of the most elegant in the history of physics. It ended the century-long dominance of the corpuscular theory. From that point forward, the wave theory became the scientific consensus. However, the narrative does not end there. A century later, a disruptor emerged. In the year 1905, a humble clerk at a patent office published a groundbreaking paper. This individual was Albert Einstein. He was investigating a phenomenon known as the photoelectric effect. What is the photoelectric effect? Simply put, when light shines on a metal surface, the metal emits electrons. No, this phenomenon was quite perplexing. If light were purely a wave, the wave's energy should depend on the light's intensity. The greater the intensity of the light, the higher the kinetic energy of the emitted electrons should be. Yet, experimental results completely contradicted this. No matter how intense the light source is, if the frequency falls below a certain threshold, not a single electron will be ejected. Conversely, if the frequency is sufficiently high, even if the light is extremely dim, electrons are emitted instantaneously. Albert Einstein proposed an explanation. Light does not behave as a continuous wave, but rather consists of discrete packets of energy. He termed these energy packets light quanta. Later, they became known as photons. The energy of each photon is determined solely by its frequency. High frequency corresponds to high energy. Therefore, with low frequency light, regardless of intensity, individual photons lack the energy to dislodge an electron. This theory perfectly resolved the anomaly of the photoelectric effect. However, it introduced a far more significant problem. If light consists of particles, how can Thomas Young's interference patterns be explained? How is it possible for particles to create interference? The answer is that light behaves as both a particle and a wave. This is known as wave-particle duality. It may sound fundamentally absurd. How can a single entity exist as two completely distinct forms? Yet, the implications were about to become even stranger. Scientists decided to verify this conclusion experimentally. They replicated Thomas Young's double slit experiment. But this time, they adjusted the source to fire in single pulses, emitting only one photon at a time. Theoretically, a single photon should pass through only one slit, resulting in two distinct bands on the screen. But the results were astounding. As individual photons were registered one by one, an interference pattern gradually emerged on the screen. How is this possible? Interference requires the superposition of two waves, with only one photon present at a time, passing through a single slit. What is it interfering with? The answer is even more radical. The photon interferes with itself. According to the interpretation of quantum mechanics, in the absence of observation, the photon traverses both slits simultaneously. It exists in a state of superposition. It is present on both the left and the right. It is both a wave and a particle. Essentially, it interferes with its own probability wave. This sounds like science fiction, but the experimental evidence is undeniable. Physicists had no alternative but to accept this reality. However, the truly mind-bending revelation was yet to come. Scientists sought to determine which slit the photon actually entered. They installed detectors beside the slits to track the photon's path. Then, a bizarre phenomenon occurred. Once the detectors were installed, the interference pattern disappeared. The screen displayed only two simple bands. The photon behaved purely as a particle. When the detectors were removed, the interference pattern reappeared. The photon reverted to behaving as a wave. What does this imply? It suggests the photon is aware it is being observed. When observed, it acts as a particle. When unobserved, it behaves as a wave. The act of observation itself alters the photon's behavior. This is the famous observer effect in quantum mechanics. It profoundly challenged the classical understanding of reality. In our macroscopic experience, objective reality exists independently. Regardless of whether one observes it, it remains constant. But in the quantum realm, this does not hold true. Observation influences the physical state of matter. Einstein was deeply unsettled by this implication. He famously declared, "God does not play dice." He rejected the idea that the universe is governed by randomness. He believed there must be hidden variables, that science had simply not yet discovered. Niels Bohr, another pioneer of quantum mechanics, disagreed. He countered directly, "Einstein, stop telling God what to do." These two titans of physics debated this issue for decades. Neither persuaded the other within their lifetimes, but the story is not over yet. In 1979, at the symposium marking the centennial of Albert Einstein's birth, physicist John Wheeler proposed an even more radical experiment. This experiment is known as the delayed choice experiment. Wheeler reasoned, since observation alters the behavior of a photon, let us wait until after the photon has passed through the double slits to observe it and see what happens. According to our conventional understanding, the photon has already made its choice when passing through the slits. It either took the left path or it traversed both paths simultaneously. This choice should be a past event. How could it possibly be altered by a future observation? Yet, the experimental results left everyone astonished. In 1984, researchers at the University of Maryland successfully conducted this experiment. The results revealed that whether the observation occurs before or after the photon passes through the slits, the outcome remains the same. As long as a detector is placed at the end, it manifests as a particle. If there is no detector at the end, it behaves as a wave. What does this imply? It implies that your present actions can determine the photon's past state. The future seemingly influences the past. Causality appears to have been broken, at least on the surface. In reality, physicists offer a more profound explanation. They state that before the photon is observed, its state is indeterminate. It is neither a particle nor a wave, but rather a superposition of both possibilities. Only when an observation is made does the wave function collapse, and the photon forces a definite state. Therefore, strictly speaking, it is not that the future changed the past, but rather that the past itself was undefined until the moment of your observation, when the past actually came into being. Niels Bohr, the father of quantum mechanics, once said, "Before an observation is made, no physical quantity has an objective existence." This statement sounds philosophical, but it is a conclusion derived from physics, and it has been verified by countless experiments. wave-particle duality is not a property unique to light. Later, scientists discovered that electrons, neutrons, atoms, and even molecules composed of hundreds of atoms all exhibit wave-particle duality. In 2013, scientists sent molecules containing 810 atoms through double slits, and the result was the same. Interference patterns appeared. The mass of this molecule exceeds 10,000 protons. It is astonishing that such a massive object exhibits wave properties. So, why do we not observe this phenomenon in our daily lives? Why does throwing a stone not generate interference patterns? The reason is as follows. According to the de Broglie formula, an object's wavelength is inversely proportional to its momentum. The greater the momentum, the shorter the wavelength. For macroscopic objects, their wavelengths are so short that they are effectively unobservable. The de Broglie wavelength of a baseball is approximately 10 to the power of negative 34 meters. This figure is dozens of orders of magnitude smaller than an atomic nucleus. At this scale, wave characteristics are completely negligible. Thus, wave-particle duality is observable only in the microscopic realm. However, this does not mean it is absent from the macroscopic world. It is simply imperceptible to us. Returning to the initial question, what exactly is light? Is it a wave or a particle? The answer is that it is neither a wave nor a particle. It is an entity that human language cannot accurately describe. We can only state that, in certain experiments, it behaves like a wave, while in others, it acts like a particle. Nobel laureate Richard Feynman once remarked, "I think I can safely say that nobody understands quantum mechanics." The Double Slit Experiment is regarded as the core experiment of physics. Feynman stated that it contains the only mystery of quantum mechanics. From the debate between Newton and Huygens, to Thomas Young's interference experiment, to Einstein's photon hypothesis, and finally to the century-defining debate between Bohr and Einstein, and finally to Wheeler's delayed choice experiment. For over 300 years, humanity has sought to understand the true nature of light. Yet the final answer reveals that the world does not operate the way we imagined. At the smallest scales, logic seems to break down, and causality becomes blurred. Reality itself becomes a superposition of possibilities. Perhaps, as Niels Bohr famously said, if quantum mechanics has not shocked you, you have not yet understood it. And this shocking world,